Just like when we first learned about derivatives, we learned some rules for simplifying derivatives, for taking derivatives of more and more complex functions. When you learned about logarithms, you learned the property of logarithms, so you could simplify logarithmic expressions. So here in section 5.3, we're going to learn about 5 rules that we can use to help simplify definite integral expressions. The first one's about order of integration. So that integral, I read it, the integral from a to b of f of x dx. That just means find the area under the f of x curve between a and b. Well, if I switch the order of the limits, so if I instead integrate from b to a, I'll end up with the opposite. I'm going to have the same shape, but I'm going to have the opposite area, and let me show you why. Here's a picture that can help us understand a little bit. So if I want to find the area under this velocity curve, I'm going to split up that area into infinitely many, infinitely thin rectangles. You can see there are 4 rectangles here. They're not infinitely thin, but you can start to get the idea. If I'm going to integrate from 0 to 4, if I use 4 rectangles, each rectangle is going to be 1 space wide, and to figure out how wide the rectangle is, I'm going to subtract 1 minus 0, and I get a distance across this rectangle of 1. I'll multiply that width times the height to get the height of the rectangle. If I change the order of integration, when I figure out the width of that rectangle, I'm subtracting 0 minus 1, and I get a width of negative 1. I'll still have a height. Now when I multiply width times height, I'm going to get the opposite of the area that I got if I was integrating from left to right. The second property, if I integrate from a lower limit to an upper limit, but those limits match, then the result of that definite integral is going to be 0. Look back at this same picture here. If I integrate from 1 to 1 v of t dt, then I'm going to have a distance across of the difference between 1 and 1. So I'm going to have a width of 0, which I'm going to split up into infinitely many rectangles. Well, every rectangle, if I'm going to have infinitely many of them, is going to have a width of 0. So if your lower limit and your upper limit match, the rectangle might have height, but it's not going to have any width, so you'll have a total area of 0. We have a constant multiplier rule for definite integrals. We had one for derivatives too. So if I want to take the integral of some function inside my integrand, whatever is inside the integral, that's called the integrand. If that's a function and that function has a constant multiplier, in this example you see I have a k here, I can factor the k factor, I can bring the k out to the front, evaluate the definite integral, and then multiply the result by k. So I could either leave the k inside the integral, or I can factor the k out, evaluate the integral, and multiply my result by that k. Again, similar to our properties for derivatives, if I want to take the integral of 2 functions added or subtracted together, I can rewrite that as the sum, or the difference, of the 2 integrals. Notice the limits will stay exactly the same. So the integral from a to b of f plus g is the same as the integral from a to b of f plus the integral from a to b of g. And then one more property, it's called additivity, and then this picture can help. If I want to take the integral, so the area under the curve from a to b, and add it to the area under the curve f from b to c, we'll look at the picture. The area under the curve from a to b is this section here. The area under the curve from b to c is this section here. If I were to add those 2 things together, that's equivalent to naming the area under f from a to c. So just notice that if this upper limit and this lower limit match, I can rewrite this addition expression as one single integral. Notice this has to be addition. This property does not work if that symbol there is subtraction. So let's try out our new rules. We're going to simplify some of these definite integrals using the information we've been given here and the properties we just learned about. So letter A, if I want to find the integral from 4 to 1 of f of x, that means the area under the f curve from 4 to 1. Notice here, nobody told me up here the integral from 4 to 1 of f. But I have been told the integral from 1 to 4 of f. And then this should be a clue here. When you see the integral from 4 to 1, those limits are out of order. We integrate usually, generally, typically, from left to right. So the fact that these limits are out of order should be our clue. And anytime you see that, I want you to think about that first rule that we learned. So we know that the integral from 4 to 1 of f of x dx is going to equal the opposite of the integral from 1 to 4. So if I switch the limits, I want to switch the limits, I'm going to have to take the opposite of the integral. So the opposite of the integral from 1 to 4 of f of x dx, which is the opposite of this part I know. I know the integral from 1 to 4 of f of x dx, it's -2. So my final answer is going to be the opposite of -2, which makes +2. Here's the next part, part B. I've been asked to find the integral from -1 to 4 of f of x. I don't know. I haven't been given that information. But notice I have been given the area under the f curve from -1 to 1 and the area under the f curve from 1 to 4. Notice that upper limit matches that lower limit. So I can use that to rewrite an expression here. So the expression I've been asked to evaluate, I can split up into two parts. And it happens to be convenient here because of what I've been given to split it up at x equals 1. So instead of integrating all the way from -1 to 4, I can integrate from -1 to 1 f of x dx. And I'm going to add that to the integral from, I'm going to pick up where I left off. I stopped at 1. I'm going to go all the way to 4 f of x dx. Well, this part, the integral from -1 to 1, I've been given. This part, the integral from 1 to 4 of f of x, I've also been given. So my final answer is that that's going to equal 5 plus, it's going to be 5 plus -2, which makes a total of +3. For letter C, I've been asked questions about both f and h, so I'm going to have to combine together all that information I was given at the beginning. So here, and what I'm going to use two of those new rules. Notice I've been asked to find the integral of a sum of two functions. And you'll notice that each one of those two functions happens to have a constant multiplier in front. So watch how I'm going to break this up. I'm going to start by splitting this up at the addition sign. So I'm going to keep my limits the same. That's going to be the integral from -1 to 1 of 2f of x dx plus the integral from -1 to 1 of 3h of x dx. This is constant multiplier 2 I can bring out to the front. So that's going to be 2 times the integral from -1 to 1 of f of x dx. Plus this 3 can come to the front, 3 times the integral from -1 to 1 of h of x dx. I'm going to look back at my paper to find this value and this value, which is going to give me an answer of 2 times. This integral we've been told is equal to 5. And this integral we've been told is equal to 7. So it's 21 and 10. Final answer of 31. All right, letters D and E are in here to make sure you're not making up your own rules. We've been asked now to find the area under the F curve from 0 to 1. Well, we've been told the area under the F curve from -1 to 1. But we can't assume that just because we've cut this interval in half, just because we're finding an area over 1/2 of the interval, we don't know necessarily that F is symmetrical. So we can't make an assumption that we're going to find an area that's 1/2 of the area we were given. So this one cannot be evaluated. There's not enough information. Similarly, letter C, that's letter E. We've been told the area under the H curve from -1 to +1. This integral asks us to find the area under the h curve between -2 and 2. But we don't know anything about the behavior of h outside of the interval -1 to 1. So doubling that, doubling that distance by stretching out the interval that we're finding there, we can't make any assumptions that h is going to have any kind of similar or predictable behavior unless somebody tells us something more about the h function. So letter E, similarly, cannot be evaluated. There's not enough information to find the integral from -2 to 2 of h.